Today's focus will be sound and its speed. So, with both sound and light, both actually travel in waves. The difference, though, is what type of wave it travels in. Sound travels in a longitudinal wave. Remember, with a longitudinal wave, the particles vibrate back and forth. If the wave is going from, let's say, left to right, they kind of like vibrate back and forth like this. Okay, that's a longitudinal wave. I always remember it as the inchworm. Okay, so if you picture an inchworm, that's how a longitudinal wave travels. If you look at a transverse wave, notice that it has that S, so it travels like the snake. It forms like an S, okay? So that's how the transverse wave travels. Now with these particles, they're moving up and down when the wave moves left to right. So sound versus light once again. Now you can't tell the difference in the waves because we can't see sound and we can't see actually the waves of light. But the main difference is we can actually tell the difference based off of speed. Light is extremely fast. Okay, so that is why for lightning, you see the lightning first and then the sound appears afterwards. Okay, because light is so much faster than sound is. Sound, though fast, it travels at a matter of 340 meters per second, whereas light travels at 300 million meters per second. So you were talking about it travels a lot faster. That's once again why we see the lightning, and then later we hear that sound, okay, that the lightning made from the thunder. All right, so the start of sound. How do you start sound? So once again, with all waves, it starts with an initial oscillation. For sound, it starts with initial vibration. So either you're adding air to a column, so like a flute, and making it vibrate. You're plucking a string on a musical instrument, or you're hitting an object. You are causing an initial vibration of the particles. So here's the movement of sound. This is how it travels. This is the longitudinal wave. Now, what I want you to note here is that these are the particles that are initially vibrating. Okay? What happens is that they, because of this initial vibration, they're going to move back and forth like this. They will then hit the particles next to them, which are these guys right here. These particles will hit then the particles next to them, then next to them, and so on and so forth, okay? So the particles that you start with right here are not the same particles that hit your ear, okay? They're just the energy is transferred from the initial particles all the way to the particles that are right by your ear right now. Now with these, because they are in longitudinal waves, you have compression areas and you have rarefaction areas. Remember, rarefaction are the places where the particles are most spread out. Compression are where they are most compressed together. So let's compare sound versus light waves because we've said in many times that they actually travel differently. So here's the image of a longitudinal wave. Here's an image of a transverse wave. So this would be your light. This up here would be your sound. Now, obviously, the waves themselves look extremely different, but for this one, what we're saying is that we've got the compression, and that matches up with always your crests, and then you've got the rarefaction, and those always measure up with your troughs. Okay, so they travel differently. Remember, it's either perpendicular or parallel to the way that the wave itself is moving, and then as a result, the image of these particles and how they're moving is also different. Okay, so once again, let's just explain how this sound moves. So with everything, you are not moving the actual particles, you are moving the energy, and those particles run into other particles, and those particles run into other particles. So here is my initial vibration. Okay, and these particles are going to oscillate or vibrate back and forth. And then when they run into these particles, then these particles will gain some energy and they'll run into these particles and so on and so forth. So then you're going to always make a compression and a rarefaction where they're moving back and forth and where you get more compressed air versus a more spread out air. And then they will keep moving until they hit your source. That's my ear. It doesn't look very good. But then we'll get these particles to hit our ear and then we will get some sound. So can you change the speed that sound actually travels? So right now at room temperature within air, it travels approximately 340 meters per second, but you can change that. How can you change it? One way is by changing the temperature. Remember, you are hitting these particles right? Okay, and the faster that they hit the next set of particles, the faster the sound will travel to your ear. Okay, so all you have to do in order to speed this up is speed up the rate at which the particles move. How can you do that? You can change your temperature. So higher temperatures, actually the particles move a lot faster, and it's a lot is relative, right? Okay, so it moves faster. So if it's hot outside, those air particles, because they have more thermal energy, those particles are moving faster, and therefore they will move the sound faster. If you lower the temperature, meaning these particles are going very, very slow to hit the next set of particles, then the sound will also move slower. Okay, so once again, if you want to make sound go faster, you do it in a hotter area. If you want it to go slower, you do it in a colder area. So explain how speed of sound changes due to temperature. So first off, I want to know which one would be the fastest. And the fastest would be where the particles can move the fastest, because then they can transfer that sound fastest. And that would be the hottest. But I don't like that color. Okay, so we're going to change it to, this is the fastest because it is the hottest. Okay, and then where would be the slowest? This would be the slowest because it is the coldest. So these particles are moving so slowly. So to go from point A to point B, it will take a lot longer than if it is extremely hot outside where the particles are moving faster. All right, can we also change sound? How else can we change the speed at which sound travels? Well, you can change the state of matter that the sound is traveling in. Okay, so sound travels a lot faster actually in a liquid than in a gas. Okay, why? Well, let's look at that once again. So how does sound travel? Remember, it's caused by the transfer of energy, here's my vibration, from this particle to all the way to these particles, right? So, or from these particles to these particles. So if you note, liquids are more dense than gases. So these particles will run into these particles at a faster rate than these particles will run into these particles to transfer to the next particles. So sound travels a lot faster in more dense substances, which are liquids, compared to gases. So if I want my sound to travel faster, I will actually make noise through water than I would through air. So in actuality, in water, sound travels 4.3 times faster than air. That's why dolphins and whales can communicate for miles. Their initial amount of energy is actually transferred a lot easier through water than if they were outside of the air. A lot of the energy from their sound and their initial vibration is lost in the air from the transfer of the particle energy to the next particles. Whereas when you're in water, the particles are right next to each other, so that energy is not lost. Okay, and then it even travels faster in a solid. Exact same reasoning. When you look at solids, they are extremely compact compared to liquids. So the solids, if I caused an initial vibration over on this side, it will not have to move very much to get to the end, right? Because each of these particles will run right away into the next particle. Whereas liquids, there is some space in between to go to the next particle, and each time they have to move a little bit of distance, they'll lose some of that energy associated with the sound vibration, so it goes a lot slower. All right, and actually sound travels 15 times faster through iron than air. So that's being iron, which is a solid, compared to air, which is a gas. So 15 times faster. All right, so now what I want you to do is identify the states of matters below. So this first guy is a solid, the second guy is a liquid, and the third image is a gas. Okay, and which one is the fastest? So rank the following in order of increasing speeds. So this would be the third, which would be gas, then comes liquid, and solid would be the fastest. Why does that occur? It's all because, once again, the particles are closest together for a solid, and they are most spread out to a gas. So it's going to take time for this energy for the gas to transfer its sound energy to another particle, whereas with the solid, it does it instantaneously almost. All right, so not all solids, liquids, and gases are of equal speed, and that a lot of times deals with its density, so how close are those particles to one another. If you look at air, which is our gas, it goes about 344 meters per second. Water, which is a liquid, is about 1,500 meters per second. And then you look at our three solids down here. So if you look at wood, wood is still a lot more than air and water, but it is not as much as iron or stone. Stone is more dense, therefore it is going to go a lot faster. The other way that you can do it is you can also change your temperature, okay? So if it is cooler, it is going to travel slower, and that's because the particles themselves are moving slower, whereas when you are warmer, the air particles are moving faster, or the solid particles, whatever it is, are moving faster, and therefore it can transfer that energy faster. So why do we care? Where in our everyday life do we care actually about that the speed of sound is different in different states of matter? And that comes all a part of tsunamis. So tsunamis, how do we even know that they're coming? Well, if we figure out with that there's like a break in the, right, a shifting of the plate tectonics. This shifting will cause an initial vibration in the land, okay? And then that will then cause the sound to travel through that land, okay? And so we can then pick it up through an earthquake detector, which we'll talk about in a little bit. And then we'll pick up that sound wave that we know was caused due to the shifting of the earth, and then we now know that a tsunami is coming. So in 2004, a tsunami killed over 230,000 people in 14 countries. And that was because some of the waves were actually over 100 feet tall, so people couldn't get away from the water in a quick enough time. So if we could detect it earlier, we would allow people more time to get away from the coast and get to dry, higher ground. So here is the image, sorry, here is the image of that tsunami. And remember, it did come up to over 100 feet tall. So if you look at it, we've got all of this huge amount of rushing of water. And if you were right here, you obviously would be dead almost instantaneously from drowning. But you just see the pure power of this huge tsunami, right? And how it was just absolutely devastating. So if you were able to get people away from the coast and get to higher ground, like let's say up here, then they would have been able to be saved. All right. So once again, why do we care? Or how do we detect it? So when you have a tsunami, it's caused by an earthquake, and that is the shifting of the land, and therefore that shifting of the land causes a vibration. Okay, that vibration is a sound. It can be that energy is transferred into sound. Okay, and so vibrations can travel faster through the earth or through the ground than it can through the water, or that the actual tsunami is going to be traveling at. And so what's really important is that we hear that sound before we actually see the wave, which gives us time to get to drier ground. So let's try to look at an image of this. Well, we'll do that in a few slides. First, how do we pick up that sound? It is through a seismograph. So seismograph detects the waves that travels through the surface of the planet. So if you look at this image, you have that shaking. You know that that shaking was caused by the plate tectonics moving, and therefore you understand that you have an earthquake, which can produce tsunamis. So let's talk about this. So this is where the fault line is, right? And so that vibration is going to cause a sound wave to travel that you will pick up through the seismograph. That sound wave will travel a lot faster through the ground. So let's say you have your seismograph right here. You will be able to pick it up well in advance, hopefully, before this wave can have time to hit and move over to the dry land or move over to land. So it's really important that because sound can travel so much faster through land than it can through water, we can pick it up hours in advance and be able to detect if a tsunami is coming, so we can move people, or a possibility, and we can move people to drier land. All right, let's talk about outer space with sound. So sound needs the medium. What is our medium? That is what the particles are that we were talking about that have that transfer the energy. So we're talking about the air particles, or we're talking about like iron particles, or we're talking about any of these particles. So they need some sort of medium in order to travel. And for that, we're talking about particles. Now, if you think about outer space has no particles. So what does that mean? Even if I caused an initial oscillation or vibration, it would have no means to travel from point A to point B because there are no particles in between. So therefore you can never have sound outside in outer space because there are no particles to be able to transfer that energy from point A to point B. So if you were asked, is there sound in outer space? No, there is not because there's no particles to transfer that energy from the initial vibration to the ending problem, the ending source of like your ears or whatever. All right, hopefully you have a basic understanding of sound. First off, I want you to understand that it's caused by initial vibration that then moves these particles through a longitudinal wave to your ears. You can speed up the sound, you can speed up the rate at which sound travels by either making the medium more dense, so a solid would travel a lot faster with sound than a liquid or a gas, and then also by changing its temperature. By making it hotter, you will travel faster. Where do we see the importance of how sound can travel differently through different mediums is with tsunamis. We use a seismograph to detect those earthquakes. Once again, finally, in outer space, because there is no medium, there is no sound. Have a great evening.